For the first time ever, astrophysicists have found evidence for gravitational waves that are light years long with really low frequencies. These are ripples through space itself caused by cataclysmic events and massive objects disturbing the space around them. Now, back in 2017, we saw the first ever detection of gravitational waves, and these ones were more like kilometers long with much higher frequencies. And we knew that those gravitational waves were coming from the merger of two black holes, just a few tens of times heavier than the sun. But this month, with all this new evidence that's been published of much longer wavelength gravitational waves, we're not 100% sure this time what's causing them. Our best guess is that it's pairs of supermassive black holes that are spiraling around each other on their way to merging. When I say supermassive, I mean anywhere from 1 million to tens of billion times more massive than the sun. But from the data released this month, it looks like that might not be the whole story, but there could be some new physics here that we could learn. So it's incredibly exciting, this result. Literally all me and my astrophysics colleagues can talk about. So first of all, if you're new here, hi, this is the channel where we dive into all of those astrophysics details, but hopefully keep it at a level that's accessible to everybody. In this video, we're going to chat about how the evidence for these gravitational waves has been found with pulsar timing arrays, how these gravitational waves are different to the ones detected by LIGO, the gravitational wave detector we have here on Earth, what the data shows us, why it's slightly different from what we'd expect for supermassive black holes orbiting each other, and also what other new physics we could learn here. So let's start with how have they actually done this. We need to break down what is a pulsar timing array. So starting with pulsars, which are spinning neutron stars. These are dead stars made entirely of neutrons. They're formed in supernova from the cores of massive stars when they die. Gravity crushes in on the core of the star that was there before and takes all of the protons and electrons in the atoms that were there before and forces them together to become neutrons, and then packs them in as tight as they can physically go in one big neutron crystal that's incredibly dense. The neutron star that's left behind actually inherits all the spin of the star that was there before, but because it's much denser, it ends up spinning way faster. Just like when an ice skater pulls in their arms to make themselves spin faster. They also have huge magnetic fields, and what that does is produces a beam of radio light out of the poles of the pulsar, which as it spins then acts like a lighthouse, sweeping that beam across the universe, which we then detect as pulses of light, hence pulsar, which can happen anywhere from like a pulse every second or so to a pulse every millisecond or so. That's how fast pulsars spin. They're essentially like clocks. You can set your watch to those pulses and they are incredibly precise. Which brings me to timing. Essentially what you do when you're studying these pulsars is you record the exact time of arrival of the pulses of the pulsar for many, many years, but you also do it for many pulsars as well, hence the array part of pulsar timing array. You keep an eye on lots of pulsars that are distributed across our galaxy, the Milky Way, in an array, all separated by different distances. Now, because pulsars are so regular, like ticking clocks, you know like what the rhythm of pulses should be from all of those pulsars across the galaxy. But if that rhythm changes slightly, you know that there's been a difference in the time between pulses from a number of given pulsars. And because speed times time equals distance, and these are traveling at the speed of light, which is a constant, if the time changes, then the distance has also changed as well. And that can either be the distance between, Earth and a pulsar, or, like a pair of pulsars in your array. Either way, you're essentially triangulating the positions of these pulsars, which should be fixed, but aren't. So what could have changed them? Well, a gravitational wave stretching and squashing space itself. Now, I know that a big point of confusion for people that I've seen being discussed on social media is how are these gravitational waves that have been detected by pulsar timing arrays different to the ones that were detected back in 2017? The first ones that we ever detected with LIGO, a detector here on Earth that uses lasers pointed down kilometer-long arms to look for, again, a change in distance. So how is this different? Well, it's all to do with the size of your gravitational wave detector. So the separation between the things that you're measuring the distance of. For LIGO, it's pointing a laser down a big tunnel, reflecting it off a mirror and bouncing back again. That's around about a kilometer long. With the pulsar timing array, it's literal light years separations between your pulsars. And that means you're sensitive to different frequencies of gravitational waves. For LIGO, they're much higher frequencies with wavelengths of around about tens of kilometers or so. And we know that those kind of gravitational waves come from the merger of two black holes that are around about sort of 10 up to 100 times the mass of the sun. But with your pulsar timing array, the separation between your pulsars is light years. So you're sensitive to gravitational waves of much lower frequencies, nanohertz, in fact, which means that you have a gravitational wave with a wavelength of tens of light years. That means between one crest of the wave and the next, you're waiting 10, 20, 30 years. So you can only detect this type of gravitational wave on these huge scales. And they're very different to the gravitational waves that we detect with LIGO. They're as different as visible light is to radio light. And in the same way, they can tell us different things about the universe. So this is why pulsar timing arrays are so useful. And it's also why people have been trying to do it for the past 20 years or so. It's why they've had to actually observe pulsars for 20 odd years, because you have to wait that long before one of these incredibly long gravitational waves actually fully passes through your array of pulsars. Now, there's been many efforts ongoing around the world to do this, and they're now all part of what's known as the International Pulsar Timing Array. But they all individually released their data and analysis last week. First up, you've got NanoGrav, the North American Nanohertz Observatory for Gravitational Waves, which used the Arecibo telescope in Puerto Rico and still uses the Green Bank telescope in West Virginia in the US to monitor their pulsars. Then you've got the Parkes Pulsar Timing Array using the Parkes radio dish in New South Wales in Australia. Then the European Pulsar Timing Array, which uses 5 of the biggest radio telescopes across Europe, who combined their data already with the Indian Pulsar Timing Array, which uses the giant meter wave radio telescope in Western India. Then finally, you've also got the Chinese Pulsar Timing Array, which used the 500-meter aperture spherical radio telescope in southwest China, which is honestly an absolute monster of a telescope. Now, they have all claimed to have found a gravitational wave background signal with their pulsar timing arrays. So not an individual cataclysmic event like what LIGO detects with, the merger of two black holes. Instead, they've got evidence for sort of like a hum or like a general symphony of just many gravitational waves of these very long wavelengths that could be coming from many different sources. It's an incredible achievement, one decades in the making that people declared, wasn't even possible as well decades ago. It's a true proof of concept that we can do this as well, and we can actually detect this background signal of gravitational waves. I really enjoyed this analogy from Katie Mack on Twitter. She said, the Earth is a ship on a cosmic sea, and every once in a while we're hit by a big wave and we know something went by. But now, for the first time, we can start to see the choppiness of the entire ocean, and we're learning what else lives in our sea. Now, the evidence they have comes from the fact that this background hum or this background signal causes correlations in your pulsar timing array data. Specifically, something known as the Hellings-Downs correlation, which essentially says that if you pick any pair of pulsars in your array and there's been a gravitational wave that's passed between them, then the delay caused by that gravitational wave to the time that the pulses arrive That delay should be correlated with the distance between your pulsars. So let's look at the data. I'm showing the nanograv data here, not for any particular reason, except for the fact that the plots are neater, and I enjoy that. And we've got two ways of representing the correlations that you'd expect. On the left-hand side, we've got what's known as the power spectrum. So the correlation in the data is shown by the blue line, and the sort of shaded region around it is your uncertainty. And then if there's a Hellings-Downs correlation, you'd expect that line to fall in the gaps of the gray violin points. So the blue line goes through those gaps, and that's the evidence for the gravitational wave background signal. There's one more line on this plot, it's this black dash line, but I'll get back to that in a second. First, let's look at the right-hand side. Here on the x-axis, you've got that separation of your pulsars against how strong the correlation is in that time delay. And it's plotted for many different pairs of pulsars at different separations. The data, again, is shown in the blue points. Now, the black dash line shows the shape that you'd expect from the Hellings-Downs correlation. And it's a pretty good fit, and it's yet more evidence for that gravitational wave background signal. It wasn't just Nanograv that saw this though. All the other pulsar timing array collaborations saw this to varying different levels of significance and sort of good fit. So here's the Parkes pulsar timing array data, here's the European and the Indian pulsar timing array data combined, and then the Chinese pulsar timing array data. And now just a little side note, because I've got some gossip for you all, right? So apparently in the collaborations themselves, there was a little bit of a disagreement between people on what threshold they should pick before declaring that this result was statistically significant, i.e. that the result had a very low probability of, just being randomness in the data. That number or threshold is referred to as sigma, the Greek letter sigma, and in astronomy, we use the threshold 3 sigma. So something has a 1 in 400 chance of just being randomness in your data. If your statistical significance is over 3 sigma, you're like, yep, I got my result, I can claim that that's real. Whereas in particle physics, they have a higher threshold. You have to reach what's known as 5 sigma. So a 1 in 2 million chance that it could just be randomness in your data that's created your signal. And apparently there was a lot of disagreement about whether they should wait for 3 sigma or for 5 sigma, because the nanograv result was at 4 sigma significance. So a 1 in 20,000 chance that the signal they've detected is just randomness in their data. So take from that what you will. But I'm an astrophysicist, I'm a 3 sigma gal, so I thought it was great to see the detection of this signal in the data. Of course, the big question is, what is actually causing this background hum of gravitational waves across the universe that we're detecting with these pulsar timing arrays? Well, let's go back to that black dash line that I ignored before on the left-hand side of this plot. This is what you'd expect the correlation in the data to look like if this background hum is due just to pairs of supermassive black holes spiraling around each other. And so if that's the case, the data in the blue shaded region should be close to the black dashed line, which for lower frequencies, it is. But above tens of nanohertz or so, they start to move away from each other, and all of a sudden that doesn't look to be a good fit. So what is going on here? Why did all the, big media outlets report it as most likely to be these supermassive black holes orbiting each other? Well, we know that there is a supermassive black hole at the center of every galaxy, and we know that galaxies merge together, and that process is very common. So pairs of supermassive black holes should also be common, especially after these galaxy mergers. Although we actually don't know if it's possible for the supermassive black holes to actually merge, because we don't know of any process that can cause them to lose enough of the rotational energy that's keeping them in orbit around each other to actually shrink their distance and merge. We know of a process that can do it when they're quite far apart still, but when they get to within a distance of around about 3 light years or so, we don't know of any process that the supermassive black holes could actually lose energy to eventually merge. This is actually called the final parsec problem. Could probably make a whole video about it actually. If you want me to do that, you pop a comment below. But aside from that, the concept of pairs of supermassive black holes is adding nothing new to our current models of the universe. We're pretty sure they've got to exist, and so that is always going to be the first point of call, going with something you know to describe what you found. And so the nanograv team looked into this too. They showed that models of these supermassive black hole binaries could reproduce this background signal that they'd seen, but not quite perfectly enough to be above that threshold to be statistically significant, like what we talked about before. Just to compare this again with LIGO, it was practically a perfect match of model from general relativity to the data that they recorded. So it was very clear back in 2017 that those gravitational waves were from the merger of two less massive black holes. Whereas in this case, it doesn't seem to be obvious at all. One option that the nanograv team actually investigated was, okay, maybe it is that background hum, but there's also maybe some pair of supermassive black holes that are nearby in a nearby galaxy that are just louder than that background hum, and that's sort of offsetting your data slightly. They did find some weak evidence that there might be two possible pairs of supermassive black holes nearby, but eventually ended up dismissing them both. So that leads us instead to taking a big leap into the unknown. Starting to consider some new physics that might explain this background signal. So these are completely hypothetical ideas that we have no evidence for yet, but if you run the maths, they should be able to generate these very low frequency, long wavelength gravitational waves. So for example, inflation, which is a period of insanely rapid expansion of the universe. We're talking exponential increase, where in just a tiny fraction of a second, the universe expanded by a factor of 100 trillion. So if you had any just tiny quantum fluctuations on individual particle levels before inflation, those fluctuations can be amplified until they're huge mega structures in the universe, which can then generate these long wavelength gravitational waves. Another option is types of cosmic strings. So these are permanent wrinkles in space itself that are a relic of, again, the very early days of the universe. But now, after the universe has expanded, they can be the size of the entire universe, even if they're only the width of a single proton. But again, they'll be big enough to generate these very long wavelength gravitational waves. Then you've also got phase transitions. So that's matter transforming from one phase to another as the universe cools. So when it was very hot and dense, you would have just had the most basic building block of matter ever, which is just a quark, right? The most basic subatomic particle. But as the universe cooled, you could then bind those quarks together to make protons. The first atoms could form for the very first time. That would have been a huge cataclysmic event in the very early days, seconds of the universe's life. And again, it's thought that could generate these very long wavelength gravitational waves. So again, the nanograv team looked at this. They modeled the gravitational wave background signal you would expect from a number of possible new physics models and compared how likely they were to these pairs of supermassive black hole binaries just being responsible for the background signal. That's what's shown in the blue points. And then also they compared like a combo of some new physics plus the supermassive black hole binaries shown by the red points. The stat they're using is called the Bayes factor, and essentially the higher that number is, the more likely that model is to explain the data than just the supermassive black hole binaries alone. And when that value starts to get in the 10 to 100 range is when people start to pay attention. And so you can see there's an inflation-related model and a cosmic string-related model that are some of the strongest candidates for new physics, seeming to fit better with that gravitational wave background signal than the supermassive black hole binaries alone, which is very interesting. This opens the door to studying the very early universe. Before gravitational waves, the only thing we had to study the universe with was light, right? Whether that was visible light, radio light, X-ray, UV, whatever it was. And so we've only been able to study the universe back to when it was just 370,000 years old with the cosmic microwave background, the oldest light in the universe, the first light given out. But it's looking like with gravitational waves, we'll have the opportunity to see beyond that, to the very first seconds, fractions of a second of the universe's life. That is a game changer. It's nothing definitive yet because there's a lot of assumptions and caveats that go into, building these new models of physics and generating what we think the gravitational wave background signal can look like. It even goes into, the supermassive black hole binary models as well. So things could still change. But there is one more test that you can do, and that is to test how isotropic the gravitational wave background signal is. i.e., is it the same in all the directions that you look? Or is it slightly different when you look over there versus when you look over there? Because if it's something to do with the early universe that's imprinted, due to inflation and then sort of like magnified to huge scales, then it should be the same in every single direction that you look. It should be isotropic. But if the signal is coming from these pairs of supermassive black holes, these binaries that are orbiting each other, then it should be different in the different directions that you look, because it'll depend on how many binary pairs are over there compared to over here. It should be anisotropic. And so, of course, the nanograv team did that test too, and they couldn't find any evidence for anisotropy. It seems as if the gravitational wave background signal that they've detected is isotropic. It's the same in all directions, suggesting it's some new physics. But as always, we can't get excited just yet. Because nanograv, for example, they only used 67 pulsars across the Milky Way. Ideally, you need more pulsars to test this properly, which is lucky because we have all of these individual collaborations that are now ready to combine their data sets. So nanograv, the European PTA, the Indian PTA, the Parkes PTA, and the Chinese PTA will all combine to give us not only more pulsars in the array, but crucially, more separations between pulsars. And if you have that, the hope is that there'll be better constraints and better statistics on fitting these models to the data. You'd hopefully be able to confirm that gravitational wave background signal at much higher confidence, so go over that 5 sigma threshold level that we talked about before, and do more tests to determine what scenario explains this gravitational wave signal best. So why this is such a big deal and why us astrophysicists are so excited is because this really does open the door to a whole new realm of studies, a new way of studying the universe. And not only that, but hopefully being able to study a part of the universe's history that we've never been able to before. Those first few seconds of the universe's life that we know so little about. We're really only going off what our theoretical models can tell us. But either way, it's either going to be down to these supermassive black hole binaries, in which case we're going to learn so much about how supermassive black holes and galaxies form and evolve together and which came first, the galaxy of stars or the supermassive black hole and the galaxy of stars formed around it, or we're going to learn some brand new physics in the next couple of years. Distance between Earth and a pulsar, or it can be the distance between, two pairs of pulsars in two pulsars. Ugh, space is hard, words are harder. Between Earth and a pulsar, or, two individual pulsars in your array of pulsars. I've said pulsars so many times. That we have no evidence for yet, but if you run the maths, they could generate these low frequency. I think I just blanked out there. I don't know what I did. I was like, that was a very long pause. My brain just was like, Call, what is this? Hello? Phone call was asking me to be on Sky News, but not talking about this, talking about Virgin Galactic or something. And I'm like, I'm not your person. Sorry. I'm trying to think if I've covered it all. There were so many papers to read. It took me so long to put this video together. I feel like I've been in this room for a very long time. I'm going slightly stir crazy.